Hi everyone. Since we are analyzing this transient response of integrator circuits, and in the previous lecture we analyzed the step response of a inverting integrator, I thought for the sake of completeness, we'll discuss the step response of an RL based inverting integrator. So in an RL circuit, the transfer function of this integrator is simply given by minus of R by SL, which can be written as minus of 1 by SL by R. So this term L by R happens to be the time constant of this integrator, and we are supposed to find out what is the output voltage of this circuit V naught after the switching event takes place. Okay, here the switching event is a step input of magnitude 10 volts is applied to the circuit, and we are interested in finding out what is the output voltage. In fact, you are supposed to find out the output voltage, the current flowing through the inductor for all time for t greater than 0, and the inverting terminal voltage as well. Okay, it's given that the integrator time constant, which is L by R, is 1 millisecond. The resistor value is 1 kilo ohm, and there is also the time constants. The initial values of the currents are given to be 0 milli and 10 milli. So we have to analyze for both these cases. So we'll first analyze for 0, and then we can easily analyze for 10 milli as well. So first step, whenever you are trying to find this output voltage, first we need to know its initial value. Initially, the step response, see, it's a step input, so initially the value is 0. Okay, then suddenly at t equal to 0, the voltage jumps to 10 volts. So initially it is at 0 volts. If this is at 0 volts, the current, steady state current flowing through the inductor, we will call it as IL0 minus. The output voltage is simply V naught, is simply minus of, here it's written here, the output voltage is simply minus of IL times R. Since IL of 0 minus is 0, the output voltage initially is also 0, right? And we discussed this in the previous lectures. I said when you are analyzing integrator circuits, you need to know the initial currents or initial capacitor voltages, especially if you assume the op-amp to be ideal. And I forgot to mention here, the saturating voltage V sat is given to be plus minus 15 volts. Okay, I'm sorry, I forgot to mention that. So if you are for integrator based circuits, you need to know either the initial voltage of the cap or the initial current through the inductor. Then you can precisely tell what the output voltage is. Otherwise you will not be able to say if the op-amp happens to be ideal. Okay, so now we found out, using this condition, we found out what the initial output voltage is. Now the switching event happens. Suddenly when the input switches from 0 to 10 volts, an inductor's current cannot change instantaneously. So meaning at that instant when switching happens, the inductor will act like an ideal current source. Okay, and the value of the current source would be 0 minus. So remember, for a capacitor we modeled it as an ideal voltage source. An ideal inductor, whenever there is a switching event, you can model it like an ideal current source of value given by IL of 0 minus. Okay, this simply means that the incremental resistance of this current source is infinity. So inductor is acting like an open circuit. Okay, so but because if it was initially carrying any current, to capture that effect, you can model an inductor as a constant current source. Now at the instant step input is applied, since this current source impedance is infinity, there is negative feedback present in the circuit, and this node voltage Vx of 0 plus will instantly come to V plus, which is 0 volts. This will be like a virtual ground. It will immediately come to 0 volts. And that will be held at 0 volts by negative feedback, by the negative feedback action of the op-amp. So now, the moment you apply a step input, now the inductor will slowly start building current. Initially its current is 0, at 0 plus it was 0. From 0 plus onwards, for t greater than 0 plus, the inductor current is given by integral of voltage across it, 1 by L integral of voltage across it, which means its current slowly starts building. That current flows through the resistor, So the output voltage will slowly start decreasing. It's an inverting integrator. Okay, so output will slowly start decreasing. You can find that expression, find the expression for it. So it will be, output will be minus of 1 by RC times integral Vi dt. So since integral is a step, so it starts from 0. So the exact expression for V naught for t greater than 0 will be equal to minus of 1 by RC integral of Vi dt starting from 0 and plus the initial voltage. Since the initial voltage is assumed to be 0, okay, because IL of 0 minus is 0, your output voltage will start at 0 and start decreasing. And it will undergo the same decrease, and the slope of this decrease is delta V is given as 10, L by R is given as 1 milli. So it is 10 by 1 milli, which is, so it will decrease at the rate of 10 volts in 1 millisecond. So therefore in 1.5 milliseconds or 3 by 2 time constants, the output will reach minus 15 volts. Okay, so remember, capacitors accumulate charge. Okay, they tend to accumulate charge. So if you push a constant current, the capacitor voltage will integrate the current. In this case, inductor's current will start increasing. Okay, its current is increasing because you have applied a voltage across it. Okay, so since you have applied a voltage across it, fixed voltage across it, the current will ramp. It will slowly start building. And if I ask you, okay, so if I ask you what will happen to the current in the inductor, it starts off at 0 milliamperes because initially it was 0. Okay, it starts off at 0 milliampere. After that, the op-amp circuit is in negative feedback, which means Vx will be perfectly at 0 volts. It will track V plus, it will be at 0 plus. Your inductor current is slowly increasing, and the peak value, it will reach a peak value when the output reaches the peak value, which is output is minus 15. So you can directly calculate, you can use the integral and calculate, but since we know the maximum output voltage is minus 15 and Vx is at 0 volts, the voltage across the capacitor, the voltage across the resistor. The voltage across the resistor is 0 minus 15 is 15, and since you know the voltage across the resistor, you can find the current through the resistor. It's simply 15 by R. Since R is given as 1 kilo ohm, it will be 15 milliampere. That's the peak current flowing in this direction. Okay, it's flowing in this direction, same as the direction of the inductor current. So the peak inductor current will also be 15 milliamperes. It will reach a value of, not the peak, the inductor current value will be at 15 milliamperes when the output voltage is at minus 15 volts. Okay, and Vx has been staying put at 0 volts because of negative feedback. Negative feedback was forcing it to stay at 0 volts for all this duration. From this point onwards, your output cannot decrease any further. Therefore, the op-amp circuit is no longer in negative feedback. I can remove the op-amp and treat the output as a voltage source. Op-amp's output is a voltage source of value minus 15. Now it's a very simple RL circuit, first order RL circuit. You have a minus 15 volt source and you have a resistor connected, and Vx is initially 0 volts. Okay, the one end of the inductor is connected to 10 volts, other end is at Vx. Now you are supposed to find out output voltage will stay at minus 15. We'll see why is that. You are supposed to find out the current in the circuit. You are supposed to find node voltage Vx. Remember, whenever you are analyzing inductor RL circuits, okay, in the steady state, the voltage across the inductor has to become equal to 0 because inductor will eventually act like a short circuit. Okay, if inductor acts like a short circuit, so whenever you have RL circuits, there will be steady state DC currents flowing in the circuit. Okay, there can be, if there is a path for it, there currents can flow. The inductor will act like a short circuit, which means this steady state node voltage of Vx is 10 volts. So this node voltage will come to 10. So I can directly, since it's a first order circuit, I know the initial value, I know the final value, and I also know the time constant, so I can plot the response. So this will happen after 3 by 2 time constants. Your circuit will reduce to a first order circuit, and Vx will start from 0 and grow to 10 volts. Now you just have to find what is the current. So initially the current was at 15 milliamperes. So that was when the output had just reached minus 15. Now what happens to the output after t equal to 3 by 2 time constants? Now look at your Vx. The inverting terminal voltage is always positive. It reaches a maximum of 10 volts. The input differential voltage to the op amp is V plus minus V minus, which is minus of Vx. Since Vx is always positive, Vd will always be negative, which means the op amp's output will stay at minus 15. So that is fine. Okay, we can confidently assume this to be at minus 15 for all time after 3 by 2 time constants. So this RL circuit steady state, since node voltage Vx reaches 10, the voltage across the resistor, if you measure the voltage across the resistor, it's 25 volts. So 25 by R is 25 milliamperes. So the final current in the inductor will be 25 milliamperes. So it starts off at 15. Remember, the current through the inductor linearly grew. At t equal to 0, it started growing linearly. And once it reached a maximum value of 15 milliamperes, from then onwards it started increasing exponentially, like a first order exponential increase. And the peak value it reaches is 25 milliamperes. Okay, steady state value it reaches is 25 milliamperes. So the steady state output voltage is minus 15 volts. The steady state non-inverting terminal voltage or the virtual node, that goes to 10 volts, and the current flowing through the inductor reaches 25 milliamperes in the steady state. So that's the response of the circuit, and you can easily plot. I mean, if you start now, this is for the case when IL of 0 minus is 0 amperes. You can easily plot the response for IL of 0 minus being some 5 milliamperes or so on. Okay, I'm not sure, I think it's 10 milli. Is that what we assumed? So we assume the initial current, 10 milliamperes. So if you assume the initial current to be 10 milliamperes, I'm sorry. Yeah. So if I assume the initial current to be 10 milliamperes, the initial output voltage V of 0 minus will be minus of IL of 0 minus times R, which will be minus 10 volts. So your output will start at minus 10. At t equal to 0, it will be minus 10. Then it will decrease to minus 15 within half a time constant, because it is increasing the output is decreasing at the rate of minus 10 volts per one time constant. So for it to reach from minus 10 to minus 15, it would only take half a time constant. In one half time constants, so within half millisecond, your output would have reached minus 15 volts. So this is half a millisecond. From this point onwards, and the inductor current would have started at 10 milliampere. Instead of starting at 0, it will start at 10 at this point, and then it will grow to plus 15 milliamperes at half a millisecond. And from then onwards, it will then do a exponential charging to 25 milliamperes. Output voltage will stay put at minus 15, and node voltage Vx will go from after half a millisecond, it will go to 10 volts. Okay, the initial condition, what did the initial condition do? What impact did it have? The initial condition, this is the initial condition. Initially it was carrying 10 milli. It just accelerated the saturating condition. No, the saturation condition previously took 3 by 2 time constants, but now within a half time constant, the output voltage saturated. Okay, so output voltage reached its peak within a half time constant. So in the same way, if I assume your initial inductor current, IL of 0 minus, happens to be 15 milliamperes to begin with, then there will be no linear charging. I mean, there will be no linear increase in the output at all. The output voltage to begin with will begin at minus 15 volts, and then it will stay at minus 15, and the circuit will undergo a perfect first order charging even after the step input. Okay, so since the inductor is already carrying 15 milliamperes to begin with, the output voltage would be at minus 15 volts to start with. V naught of 0 minus will be at minus 15 volts, and it will stay put at minus 15, and the inductor current will now go through a first order charging increase. So it will start at 15 and then it will go till 25 milliamperes. That's it. That's the only difference here in the circuit. Okay, so in the next lectures I'll finish off these discussions of integrators. So some of you wanted more practical content. I will definitely cover it. See, my intention is I'm also keeping circuit designers in mind. So therefore, all these, the analysis is very useful when you're actually building practical op-amp based circuits. These analysis skills will come in handy. Applications, then we can also, we can very easily, you will be able to very easily understand applications once I start talking about, regulators and all the other circuits. So that's not a problem. These skills are very important. How to think when you are solving these circuits. Okay, both inductor based and capacitor based circuits, these are very useful. So don't think that this is all a waste. It's very useful. So I'm sure that you'll find it you will find it really useful. Okay, thank you.